Okay.
I guess you're hoping some of you are done. If you are done, feel free to pass it over. Oh yeah, no worry. If you're not done, I won't rip it out your hands yet. Don't worry.
I walked to your class again this morning.
You what?
I walked here and it was working at 7:50.
Oh. Because you prefer that to Dr. Brad, or?
No, I just saw it. And then I
Oh,
called
that's right, yeah, it is like Tuesday, Thursday.
And I called Reagan and I was like, hey, let's try to find my ID so I couldn't get into the building, to the wrong building. So then I was late for the class that I was not even supposed to be at. And then I was like, well, now I have to walk across the.
You're all set? I'm not rushing you. I think we got them all now. Yeah, if you ever want to get in here at 7:50, you can come, just bang on this window and I'll be like, go away, and you'll know to go to Dr. Brad's.
Okay, yeah, but that's.
Embarrassing? No.
No, because I enter right as class starts.
Oh, okay.
So.
Oh, so then it's too late already. You could set an alarm on your phone and say, go to faculty. All right, it's my fault for having class in this building, so I'll take the blame. Okay, let's do this. It wasn't too hard, hopefully. You're just counting up the things. So you got this probability distribution. Here's mine. So I just did the multiplication. 1 times 1 is 1, 1 times 1 is 1, 2. And these are all equally likely. So there's 24 different equally likely outcomes. And then you can do the math, count them up. 1 out of 24, and then 3. You've got this interesting pattern. There's probably a formula. I didn't bother trying to come up with it. So there you have it. Okay, today we get to talk about grade expectations and variances, but mainly expectations. And so this is an expectation is just the expected value. This is just the average outcome. So the average outcome over time, over time. So if we were to do the same experiment over and over again, I'm not going to do this, but I could, couldn't I? I could take all of these dice. It would be the same as rolling the same die over and over again. I could take these and just roll them, all these the six-sided dice, roll them all, and that's like rolling the same die 20 times, or however many I have here. So what is the average? What would you predict the average to be if I did that? That's what the expected value is. So it's kind of like the expected, like if I were to do this over and over again, what can I expect? What can I expect? That's the deal. So it's actually quite easy to compute the expected value, but to do that, let's talk about this situation. How would I compute the average for this situation? If I rolled them, I've got them all here. Does anyone want to tell me what to do? How do I compute the average outcome of all these dice?
Add them all up.
Add them all up?
Divide on the dice number.
Oh, yeah, that's a good idea. Okay, so let's, you know what, to make it easier on myself, I'll separate it out here. These are all 1s. These are all 2s. Here's the 3s. Here's the 4s. Here's the 5s. And here's the 6s. So what I just did there is I separated them into groups based on their outcome. And so theoretically, though, you could predict, I know that I have more 1s than I would have expected, right? And this is the expected value. So theoretically, you would expect them all to be the same number, right? Because they're equal probable. They're the same probability for each number. So let me just pad this a bit. Oh, here, I'm just going to cheat. Turn this over. So I would expect there to be the same number of 1s. I've got 4 1s. And this as 3s, so there's 4 3s. And I would expect the same number of 5s, so now I've got 4 5s. And I would expect the same number of 6s, so there's 4 6s. Once again, this is, I'm cheating a bit, but we do this when we're trying to figure out a math problem. So there's 4 4s and 4 2s. Okay, so now I've got the same number of each. And this is what you would expect over time. If I were to do that with 1,000 dice, You have some variability here, but with 1,000 dice, or better yet, 6,000 dice, you would be surprised if you didn't have around 1,000 of each number with 6,000 dice. Then if there was anything other than about 1,000, maybe 998, maybe 1,005, but there's, within reason, within a little bit, you're going to have the same number of each number. So it's the average over time if you have a whole bunch. And so maybe a good way to do this is instead of adding them up, well, we could add them up. So here, let's pretend that we're going to add them up. So you have 1, 2, 3, 4, 5, and 6. And maybe I could write it like this. I have 4 of each. 4 of each. And then if I were to add these up, there are 4 1s. And so that's going to be 4, a total of 4 pips on the 4 1s. And then 2 4s. When I get done adding up, 4 2s. When I get done adding up all those 4 2s, that's a total of 8. So I'm just sort of doing this the way you might have done in statistics class when we had a frequency distribution and had to come up with the average. And then you could do the same thing with this and this and that, so that each one of these just represents the total of adding up the values of the 4 6s. So 4 times 6, instead of saying 6 plus 6 plus 6 plus 6, we're mathematicians, we can handle adding those up. Add them up, you get 24. So add up all of this, what do we get? Just a minute. So that's 20, 40, 60, 84. Did I get that right? I hope so. Anyway, so there's 84 is the total of all of that stuff. So all of the numbers that are showing right now, and I cheated, but we're doing a theoretical sort of expected value, not the real actual average. It's what would we expect. So we got 84, and then let's add up how many dice do we have there? Oh, there's 24 dice, right? Because there's 4 times 6, 24 dice. And so then we can just do this. 84 divided by 24. And what do we get here? Is that 3.5? Yeah. 3.5. Excellent. Okay, so let me just see if we can do this a little bit quicker. So notice that you're dividing by 24, which is 4 times 6, right? 4 times 6. So I could have, instead of dividing the 84 by 24, I could have divided earlier. I could have done this. 4 out of 24, 4 out of 24, 4 out of 24. And you might say this is way more work, but it actually is going to be better for us in the long run. So this is over 24, 24. After you multiply, so notice I've lumped in the 24 with the fraction here. So 1 times 4 24ths is 4 24ths. Then 2 times 4 24ths, 3 times 4 24ths is 12 24ths, and so on. And then when I get down to the bottom here, instead of adding those up and getting 84, I add them up and I get 3.5. So 3.5 is what we call the expected value for a 6-sided die. Expected value, we're going to write like that. And it just means that if you were to roll a 6-sided die enough times, then on average, you should expect it to come up, well, an average of 3.5. And nowhere on this die is there a 3.5. They're all integers. And yet, this is the average. And this always bothers our stats students. The statistics students, they don't like it when averages come up to be decimals. When, like, if I say the average number of siblings, for a group is 1.7. Like, oh, that's terrible. You can't have 1.7 siblings. But you understand this, that it's an average. This is an average. Sometimes we use the Greek letter mu, which you're all familiar with, right? Greek letter mu is like the average of a population. So we'll use that here as well. Now there's a formula for average. Do I have it here? No. I probably have it here somewhere. But let me just put it over here because this is more fun. Okay. I have some other stuff up there. But here's the average. The average formula, E of x. E of x is literally this, the sum of all of the outcomes in a random phenomenon of x times the probability of x. Okay, so we got to demonstrate this with a couple of things. Let's flip coins. Let's flip 3 coins. And then we'll talk about fairness in games. I probably should have done the fairness first. Too late now. The cat's out of the bag. Okay, so flip 3 coins. And I want to know what is the, where x is number of heads. And I want to know the average number of heads that you can get on 3 coins. Is my microphone on? I guess it is. It's hot. Hot mic. Let me see if I can cool it down a bit. Testing? Okay, that's a little better. It's just up in the red zone. Okay, flip 3 coins, average number of heads. So let's see. Here's how we could do this. We have x and p of x. So we're going to make this same sort of a chart like we did for homework today. And you can all do this. In fact, I have confidence in you. And so why don't you go ahead and do it while I get myself set up here to take attendance, which I have not done yet. There we go. Probability. Submit. All right. I have done my duty. All right, Reagan, what are the different outcomes that you could have when you flip 3 coins and you count the number of heads? Oh. I just was, she's probably watching this like, I know. Okay, Alyssa, sorry, next volunteer. Sorry about that. What are the different outcomes you could have?
0, 1, 2, and 3.
Very good, yeah, so you could have 0, 1, 2, or 3. Now, if you had said 0, 1, 2, 3, and 4, it's okay, sort of, because you could have 4. The probability of having 4 is 0, okay? So you could put 4 on the list, but it's kind of superfluous. Okay, Nolan, what is the probability of getting 0 heads with 3 coins?
0 heads?
Yeah, no heads. Okay, well maybe I'll make it easier for you here. What's the number I put on the bottom of this fraction? How many ways can you flip 3 coins?
3 times.
Yeah, you're going to flip a coin 3 times.
Oh, is it 9?
It's not 9. So how many choices do you have for the first coin?
Oh, hesitates to 2.
2. And then what about the second coin?
Is it 8?
It is 8.
Yeah.
Good job. Okay. Excellent. Now let's find the next volunteer and we'll get the top. Zane, do you know how many ways you can have 0 heads?
Just 1.
It is just 1. Yeah, it's just tails, tails, tails. Okay, almost done, and then we'll be able to calculate this thing. Sydney, what about the probability of getting 1 head? Do you know that? So it's something over 8. So I'll get these set up here. What was that? 3? Yeah, very good. Sorry, my hearing isn't what it used to be. So 3 out of 8. I'll do the others. Yeah, that's, by the way, 1 head would be this. Heads, tails, tails, heads, tails, and tails, tails, heads. So those 3 out of the 8. There are exactly 3 ways you could have 2 heads, and there's exactly 1 way to have all 3 of them be heads. Okay, now that we've got that squared away, the next thing you're going to do is compute x times p. So that's easy there. This is 3/8. This is going to be 6/8, and this is going to be 3/8 as well. So I'm just taking each of these and multiplying them by their probabilities and adding things up. And then now we're almost done. The last step is add these up, and that's going to be the expected value. So expected value is what you get when you add those up. That's 12/8 or 1.5. So another one that ends up in the middle. It's kind of boring, but it's the way it goes. All right, so this isn't too bad. Now I've got to give you one to do, and I'll do that, and then I'll go hunt through my PowerPoint to see where I am because I have gone off the rails now. So here's what we're going to do is we're going to draw, how about 5 cards? 5 cards from a standard deck. Okay, so, and I want to let x equal the number of hearts. Okay, so I'll get you started on this. So here's my table. We have x, I have the probability of x, and then once I've got that, I'm going to multiply the two together, and then I'll add them up. Okay, so I think you can probably figure this out, but you can either have 0 heads, hearts. No, this is going to be too much work. I mean, you could do it. It's not that hard. Let's not have 5 cards. Let's do 3 cards. I know, you've already finished the problem, and now you got to go do it again. No, I'm just kidding. So just change it to 3 cards. That'll be a little bit easier. So you've got 3 cards. You can either have 0 hearts, or 1 heart, or 2 hearts, or 3 hearts. So those are the only options. This will be a little less computationally intensive. So go ahead and do that, and then I've got to regroup on my PowerPoint because I don't know what I did. Well, I know what I did. I decided to ignore the PowerPoint, and now I pay the price. So let me go back, see what I'm doing. Okay. All right. Oh, we're doing okay. Here's where we are in the PowerPoint. Although the PowerPoint is poorly written, well, not poorly. It's designed poorly. So here's where we are. You can't read the bottom part, but the way you compute an expected value is you make a table describing the distribution just like we're doing. Multiply each outcome by its probability, which we're doing, and then what you can't read down there is add up the results. So add them up, basically. So we're doing okay. Just wanted to make sure I caught all the little examples that I had. So we'll get back to the PowerPoint examples momentarily. This one's good, though. Got a deck if you need it. Okay, let's do this. I've got my deck of cards. So if I deal out 3 cards, and let's shuffle just to make it legit. So shuffle the cards and deal out 3. Well, I'll cut first. 1, 2, 3. And I want to know what are the different outcomes that I could have in terms of the number of hearts. So I'm not looking at these. I can prove it to you. There they are. They're right there. They're there. So what are the different outcomes that we could have down there with those 3 hearts? Here, I know you don't want to say it, but Zane doesn't mind telling me. What are the different, never mind, I've got them here. Zane wants to tell me about the probability of no hearts, right?
Sure.
Yeah, let's hear it.
Is it 1 out of 64?
Okay, so how many cards are in a deck? 52, and how many are you choosing out of those 52?
3.
Very good. So it's 52, choose 3 is on the bottom of this thing. And I want none of them to be hearts. So Chelsea, if I don't want any of the hearts, do you know how many non-hearts there are in the deck of cards? Very good, which is 39. So 39, and so you're picking 3 of them. You want all 3 of them not to be hearts. So this will be 39, choose 3 up here, and then 52, choose 3 down there. All right, very good. So that's the probability that none of these cards are hearts. And now, of course, well, we'll get there in a minute. Okay, now let's deal with the probability that exactly one of them is hearts. Once we get this, the rest of it will be easy. So we're at Cooper. Cooper, what is the probability that exactly one of them is a heart? Now, I'm going to guess that you're going to tell me that the denominator is also 52, choose 3, and you're right about that. But what about the numerator? I need 1 heart and 2 non-hearts. How do I count that?
I have just 1, 4, times 39 over 52 times 38 over 52.
Ooh, oh, okay. Okay. Let me write that down. 1/4 times, what was that again?
39 over 52 and then
Uh,
38 over 52.
Okay, I don't like the 39 over 52. Sorry. I'm going to put it over 51, and I'll explain why in a minute. But I like your 39 and your 38. I love them. Okay, so we'll come back to that way of thinking. This goes back to that idea that there are more than one way to compute probabilities. That's probably why it's so hard, because we forget that there's more than one way, and then you start just making up your own way that doesn't make any sense. Let me come back to that. So we'll go back to the Cooper method in a minute. But let's get back to if we're choosing. So did anyone do it with the combinations instead of what Cooper did? What did you do, Rachel?
I did 13 choose 1 times 39 choose 2.
Okay, that works. So this is 39 choose 2. So if you do it that way, you're going to choose one of the hearts and then multiply that by choosing 2 of the other cards. Now let's go back to Cooper's way. I liked it. I liked it, but now I don't anymore. Do I not like it anymore? No, I still like it. I think it's the same. Oh, I'm going to have to do the calculation now. Okay, let's check. Let's double check to see if it's exactly the same, then I'm good with it. So we have my method, which is the same as Rachel's, and some of the rest of you was 13 times 39 times 38 over 2 times 1, all over 52, 51, 50, all over 3. It's not quite the same. Drat. Sad. Okay, I think I understand what's going on here. Okay, so those cancel, and I've got 13 times 39 times 38 times 3. Hold on a minute. 52 times 51 times 50. So this, by the way, this is 39 choose 2, this is 52 choose 3, and this is 13 choose 1. Okay, so that's what I'm getting after simplifying, which isn't exactly the same as what Cooper has. So I like your thinking, Cooper, but I think that since you're thinking in terms of permutations, we need to add in this additional multiplication and say that your heart, since you want one heart, it can either be the first, second, or third card. So that's why there's 3 there. So you have 3 options for which card is the heart. Then you choose the heart, which is a 13 out of 52 chance. Then you choose the other 2 cards, and that's those 2. So yeah, I like it, but we want to make sure it's right. Okay, so there's that. Wow, this is way more work than I thought. Number 2, what's number 2? So what's the probability of having 2 hearts? Oh, here, let's find. Now that let's use my method. You could use the Cooper method, but let's stick with combinations. So stick with this on the bottom, 52 choose 3. Jaron, what would you put on top of this?
13 choose 2 times 39 choose 1.
Very nice, 39 choose 1. By the way, this sort of probability is going to pop up next week. We're going to name it. We have a name for this kind of a probability, and then you're going to say, oh, it's that kind of a probability. It's always going to look like this every time. Okay, last one, 3. If I want 3 hearts, I think you can probably figure this out yourselves, but let's get it. Hannah, what do you got for 3 hearts? I'll put the 52 choose 3 on the bottom.
And then I had 13 choose 3.
Yeah, because you just want all 3 of them to be hearts. Perfect. Now we just multiply, so that's the next step, is multiply. That was easy. This one is harder. Okay, the next one's even worse. 2 times 13 choose 2 times 39 choose 1, over 52 choose 3. Ugh. I always put a line there because we're so used to that. Okay, and then the final one, 3 times 13 choose 3 over 52 choose 3. Okay, and then we would add those up to get the total. And then that would be it. Okay, phew. Okay, so normally I have lots of gambling. Yeah, you'd add those up. It's too much money. I could do it on a calculator. You could do it later. What was it? One heart. One heart. Okay. Normally I have lots of gambling examples when we're doing this. For example, pick three. Let's just do that one real quick, but I want to get on to life insurance. So pick three. Pick three, what you do is you pick 3 digits. That's what it is. This is the lottery, by the way. Lottery. By the way, I'm opposed to the lottery. I'm opposed to all gambling. And it's for reasons that may be different from whatever church you go to would claim to be the reason to be opposed. My reason is because in Isaiah we're told that we should not make laws that unjustly harm the poor. And in general, the people who are harmed the most by gambling in any form are the poor. And so we really should avoid all gambling, or at least not, like, legalized gambling is horrible because we are doing exactly what Isaiah says not to do, and that is we have made a law that harms the poor. So right there, we shouldn't do it. Okay, but getting back to pick three. Great example, just because it's easy to understand. Pick three, you pick 3 digits. And if your 3 digits are the same as the 3 digits chosen at the end of the day, each day they have a pick three, you get, how much you get? $500. $500. You pay $1 to play, you get $500 back. They may have raised the prices, but it's the same ratio. So it may be that it's pay 2, you get 1,000. But whatever the situation is, pay $1, get $500 back. I'd like to know what the average outcome is. So in the pick 3 lottery, what are the outcomes? Well, the outcomes are actually dollar amounts. So it's what's happening to your wallet. So X is going to be your wallet. You either lose $1, that could happen, or you gain $500. Oh, hold on a minute, wait a minute. They don't give you your dollar back. So technically you don't gain 500. You only gain 499. So let me correct this. So if you're playing pick 3, you're actually only going to win $499. 499. Okay, so the probabilities. So pick 3, you're going to pick 3 digits. This is actually quite easy. Those are the bars for the fractions. So I'll bet you could figure out, take a guess as to the probability of winning the pick 3. So that would be this down here, win. And this is lose. So what is the probability of winning? Does anyone know offhand? You're picking 3 digits. So you could say, how many choices do you have for each one? How many ways? What do you think?
1 out of 1,000.
Yeah, 1 out of 1,000. There's 10 choices for each digit. So that's 1,000. One way of winning out of 1,000. There's 999 ways of losing. And so let's go ahead and multiply these together. This is negative 999 out of 1,000. And this is 499 out of 1,000. Add those together. And on average, every time you play, you lose 50 cents for every dollar you play. It's terrible. I mean, what a horrible tax. Every time you play. Now, I remember I was in Philadelphia, and talking to this guy who's like, yeah, I play the lottery, I just do it for fun. So, it's okay. I win sometimes, I lose sometimes. I said, do you ever keep track? He said, no, I just win sometimes, I lose sometimes. If he had kept track, he would find that on average, he would lose a 50 cents for each time you played. Now, let's contrast that just for a minute with something like roulette. Roulette or any other gambling game at an organized casino. Roulette has average outcome of about a nickel. You lose a nickel for every dollar you play in roulette. Lottery, it's 50 cents. Almost every lottery game is 50 cents on the dollar that you lose. So I guess if you have to gamble, I'd say go to Las Vegas and do it in a casino, because it's better than going to doing it, like that. By the way, we didn't get to life insurance, but life insurance, you're basically gambling, right? I'm paying money, and I'm gambling that I'm going to die. Because if I die, then I get the big payout, right? And if I don't die, I lose. Wait, that's confusing, isn't it? But anyway, you can do the calculation in almost exactly the same way, but I do support having life insurance, especially if you have young children. So, I mean, that's the real reason to have life insurance. That's the only, I don't have life, well, I do have some, but I don't have as much as I used to. Back when the kids were young, I had almost $500,000 life insurance. Now it's like 100,000. I don't need it. All right, I'm going to stop the recording if you want to chat. Otherwise, there's homework. You can figure it out. We'll see you on